In the previous notebooks, we implemented a multilayer perceptron for the XOR dataset. Let's now get to a slightly more challenging problem and implement a multilayer perceptron for the MNIST handwritten digit classification dataset. We will be doing this in multiple parts, and in this first part, we will be inspecting the dataset first. As usual, we will start with loading the dataset. So if you are curious about more details about the MNIST dataset that we are going to use, here is the official website link that I will include in the notebook for future reference. However, here we are not going to fetch the data from the website ourselves. We are going to use a data loader and dataset utility from PyTorch. So here we are using datasets.mnist, and it will automatically load and format the dataset for us. And this dataset is analogous to the custom dataset that we have defined in the previous videos, and we will actually learn in future videos how we can create our own MNIST dataset class. But yeah, here for simplicity, we will be using this built-in function in Torch Vision. Okay, assuming this has finished downloading, let's just inspect the number of training examples. So in this case, we have 60,000 training examples, and we have 10,000 test data points. Like before, it might be a good idea to now create a validation split from the training set so that we have a validation set that we can track during training. So for that, we are going to use the random split function in PyTorch. So we are calling random split on the dataset here, and we split it into 55,000 training data points and 5,000 validation set data points. And then just like in the previous video, we will be using the data loaders in order to load the data using a batch size of 64 here. As I mentioned many times before, it's a good idea to check the label distribution in the different subsets. So let's do that and see what the label distributions look like. For that, we are going to use the counter class implemented in Python's standard library collections. So what we do is we initialize this train counter object using counter, and then we are iterating over the data loader here, the training data loader, and then we update it with the labels in this data loader. So this will create a count dictionary, which we then print using this command. And yeah, here we are doing the same thing for the validation set instead of the training set, and here we are doing the same thing for the test set. So let's see what the numbers are. So as we can see here, we have 10 labels, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. These are the class labels. And the second value is the counts. We have 5,419 data points corresponding to class label 0, 6,000 so-and-so corresponding to class label 1, and so forth. And while this data set is not perfectly balanced, it's reasonably balanced. So there are different numbers of digits or class labels for each class, but they are roughly the same, and this is just fine for deep learning. So in practice, what I also like to do is to implement a zero rule baseline, essentially a majority class classifier. It's called zero rule classifier or majority class classifier. This is just to double check what the performance is if we always predict the class that is most frequent in our dataset. So let's do that here. So what we do is we use the test set and we just obtain the most common class here, the majority class. And the accuracy, when we always use that class, so we count the number of instances that we have from this class and then divide by the total number of data points in this test set, what we get here is 11.35% accuracy. So if I would not use any classifier, if I would always predict the class label 1 here, then I would get 11.35% accuracy. And this is always a good sanity check. Sometimes you have a label distribution where you have, let's say, 90% of data points from one class, then achieving a 90% accuracy is not a big challenge. So in this case, it's always a good number to know because you really want to outperform this number using machine learning or deep learning. If your deep learning or machine learning classifier is worse than this number or not significantly better, that's a bad sign. Okay, now a last little check here before we move on. So let's do a little visual check to see what the data actually looks like. So here we are going to use a utility function from Torch Vision again, where Torch Vision is really like a partner library of PyTorch for specifically computer vision models like image classifiers and image datasets. So here we are going to use the Torch Vision utils make grid function, which will create a grid. In this case, an 8x8 grid, because we have 64 images we use here. So it will do an 8x8 grid of the images, of some random images of the training dataset, just to see how these images look like. And yeah, this is the dataset we will be working with. You can see there are many instances of the same handwritten digits, but they all look slightly different. And in the next videos, we will of course then implement our classifier to classify images in this dataset. So in this notebook, we loaded the MNIST dataset and did a quick visual check. And in the next notebook, we are going to implement the multilayer perceptron that we are going to train on this dataset.